Hi, this is Pat Capello. I'm solving problem number 10 on page 66. This is a vector addition problem. The problem reads, three vectors are shown in figure 332. Their magnitudes are given in arbitrary units. Determine the sum of the three vectors. Give the resultant in terms of A, components, and B, magnitude and angle with the x-axis. Solving this problem involves using some of the trig methods that we've been learning in class. You can see from the sketch here that I've drawn in the three vectors just arbitrarily. I didn't measure. And the first thing you have to do is step one would be to resolve the vectors into x and y components. So I'll start with that, resolving into our components. My x component of vector A is going to be the magnitude of vector A times the cosine of the angle theta. And so therefore I can write A, which we know is 44 units times the cosine of 28 degrees. So I'm going to do 44, again, arbitrary units times the cosine of 28 degrees. And the y component of vector A is going to be A times the sine of the angle theta here. And I'll multiply 44 times the sine of 28 degrees. When I run those through my calculator, I get 38.8. Again, no units. For my x component and for my y component, I get 20.7 units. I'm going to do the same thing for B. There's a slight difference in what's happening here in vector B. As I take a look at vector B here, you should recognize that if I were to graphically resolve that, we would find that the x component of vector B lies along the negative x-axis. So I'm going to have to keep that in mind. Notice that the angle that they gave you references the negative x-axis, so it's acute. If you just punch that into your calculator, it's going to think you're in the first quadrant, and it's going to give you a positive value, so you'll have to deal with that. Of course, I've gone ahead and drawn in the y component as well. All right, let's go ahead and run these numbers. We get b times the cosine of the angle theta. That's going to be, our magnitude b is 26.5. And I'm going to multiply that times the cosine of the angle that's made with the negative x-axis, which is 56 degrees. And the y component of vector b is simply b times the sine of the angle theta, and we get 26.5 times sine 56 degrees. Running those both through my calculator, I get 14.8 for the x component of vector b, and for the y component, I get 22 units. Vector c, oh wait, I talked about this negative piece and then almost forgot it here. So we can see here that this b component is in the negative direction. I should say the x component of vector b is in the negative direction. So I have to be very careful there to give that 14.8 x component magnitude a negative direction. Moving on now to vector c, I don't need to run this trigonometrically. You could, and you would still get the right answers. You could write out c cosine theta and c sine theta. But you can also just, by looking at the vector c, that this is directed along the negative y-axis. And so therefore, all of the magnitude of 31 is directed in the negative y direction. So cx is 0, and cy is negative 31. So those are my components for A, B, and C. Step 2 of this problem is basically finding the resultant. So the x component of my resultant is simply all of these x pieces, ax plus bx plus cx. So I'm going to get 38.8, and I'm going to add to it negative 14.8 units. And when I add those two numbers together, I'm getting 24. And the y component is found by adding all of the y pieces together, 20.7 plus 22 plus negative 31. When I add all the y pieces together, I get 11.7. for part A asks find your resultant in component form. That right there would be sufficient. I could simply say Rx is equal to 24 and Ry is equal to 11.7. But part B asks you to describe it in traditional vector form, which is magnitude and direction. So to answer part B, I need to find the magnitude of my resultant, which I can use the Pythagorean theorem for. First, before I do that, let's go ahead and sketch in my resultant components. Positive 24 units is my x, my Rx here, and positive 11.7 is the y component of my resultant. That means that I should have a first quadrant vector somewhere between 0 and 90 degrees. So that'll come into play when we're dealing with the angle. So finding the resultant, I'm going to use the Pythagorean theorem. If this is my resultant here, the sum of the y and the x pieces, I should pay attention here to this right triangle that's created, where the opposite side of that triangle here is ry, the adjacent side is rx, and the hypotenuse is actually r. I'm looking for r in this case, the hypotenuse of the triangle, where these two pieces are known, so I can just use the Pythagorean theorem and say that r squared is equal to rx squared plus ry squared. Solving for the magnitude r, I can take the square root of rx squared plus ry squared. And then finally, I can now say that the magnitude of r, after substituting those numbers in, well, let me go ahead and do that. Root 24 squared plus 11.7 squared. And finally, once I run that through my calculator, the magnitude of my resultant is 26.7 units. The last piece here is finding the angle theta. Again, I can use the tangent function. We know that the tangent relates the opposite and the adjacent side, or in this case, it's the ratio of ry over rx. And I'll take the inverse tangent of both sides. And I get theta is equal to the inverse tangent of 11.7, which is my y component of the resultant, divided by 24, which is the x component of my resultant. And I get something just under 26 degrees, like 25.8 or 9. Let's see here. So since I'm dealing with 25.9 degrees, I'm going to leave that with 3 sig figs because all of my initial units were given to me in with 3 sig figs. If you look up here, my initial data, I did truncate that to 2 sig figs, but the book does give it to you with 3 sig figs. So the final answer is my resultant is 26.7 units, comma, 25.9 degrees. And there we go for problem number 10.